Um, we'll begin today, as we normally do, with a retrospective on the previous day, and we'll then continue on to talking about a fairly wide variety of different materials today, in addition to working towards the project. Um, so, in yesterday's material, we took an overview of two major topics. The first of them sought to discuss some of the different types of dynamic modeling that are widely applied in the health space, and in particular focused on three, namely system dynamics modeling, shown here, with dots and flows, where we describe a population divided into a set of health categories, health and attribute categories, and we examine its evolution over time. It gives us a cross-section depiction over time of the evolution of the health of that population, with a particular focus on the mechanism called feedback, cases where a change at one point in the system ripples around to yield a cascading series of changes that either amplify or push back against that original change. This sort of modeling is very well suited at an aggregate level to understanding broader technical populations, but does have limitations in the degree of precision with which it can represent certain causal pathways, the degree to which it can represent history dependence, effects such as networks, etc. We also have been discussing, of course, in this context, agent-based modeling, and we had highlighted some of the strengths that agent-based modeling brings to the table, as well as some of its limitations. You've heard me mention this several times before, and so I won't go into it in detail, but there's a set of texture trade-offs between these multiple methods. Agent-based modeling does have areas where limitations are obvious. Among them, the somewhat stronger skill sets that are required to apply it, and some dangers associated with the flexibility that it offers. As well as the fact that the models are not analyzable formally, which for some people is quite important for the sorts of insights they look to gain, very general forms of insight. The other type of modeling we looked at was discrete event modeling. Here we're particularly interested in workflow-driven systems, which are defined processes associated with them, where resource constraints limit the processing that goes on. So, for example, the availability of piece of diagnostic equipment, availability of a clinician may materially affect the rate at which someone progresses through a healthcare process, as we can explain. And when resources are not available, people queue up for that resource automatically within the discrete event model. So they're very well adapted to representing the impact of resource shortages and the flow of individuals through the system. And as such, they're a very popular tool in the complex system toolbox for investigating care pathways, particularly within a facility. So widely applied, for example, in trying to understand the impact of placement of resources within a facility, the availability of the quantity of those resources on quality and delay of experience by individuals. Within this context, we have a very structured representation of the care process, and it really shines in areas where that's a good match. What does not capture very well is interaction between stages. The typical interaction between those flowing through the system here is typically limited strictly to interaction vis-a-vis of resource consumption. In other words, the fact that one person is in the ultrasound scanning area may mean that another person has to wait. And that's the limit of the interactions that are typically captured within these models. In other words, it's a resource constraint type perspective, rather than directly representing how one individual interacts socially with another or infects them or what have you. So these sorts of discrete event models are highly suited to representing structured care processes, but exhibit real challenges if you try to represent the broader health of the population from more of a population health or epidemiological point of view. They form the third major type of modeling supported within the package we've been examining, AnyLogic, and the third major type used within the health area. So those were three types that we saw last time, and then I thought to provide some rules of thumb from my own experience, applying dozens of health modeling projects. Sort of what do you look for different approaches? What are sort of key features of a situation that might push you towards one type of approach or another, either for a whole modeling project or as pieces within a given model. Here we have the luxury in AnyLogic of weaving together pieces that are drawn from each of these approaches into the same model. So we can have a representation, for example, of people's encounter with an emergency room in a discrete event model, but the actual characterization of individuals in the population might be couched in a system-dynamic or agent-based model. But there are certain features, textured aspects of the situation which would recommend one approach versus others, and I've listed them here. Naturally, with AnyLogic, it's going to encourage very easy coupling of these approaches. It tends to put an emphasis on lowering the barriers between combining them. So within this version of AnyLogic that we've been using, every agent can flow through a care process transparently. We call the quantities or the people flowing through a care process entities, and every agent is an entity. So they can directly present for care and flow through a defined care process. Within this context, I did gloss over certain details, and one of them was the very rich way in which our particular passage examined here, AnyLogic, allows you to capture spatial movement of individuals. And for those concerned about the movement of, say, agents within the context of a facility, maybe it's a clinic, maybe it's a building where vending machines are located, maybe it's a larger hospital. There's a definite potential for representing within a discrete event context the movement of individuals through that organization. AnyLogic makes this very easy. You can define movement pathways by which individuals move about the facility and which lead to their exposure, for example, to different risks, or that lead to their interactions with each other as agents, if you were to hybridize it. And I'll give as an example of this, there's a model which I believe I've given to you. It's a model that involves ophthalmology, an ophthalmology sort of example where we have people circulating within the context of an ophthalmology clinic. And I am having trouble finding it here, so I may have to punt on that. But people fundamentally will circulate through a clinic. You define paths, you lay them down on the actual map of the facility, and you basically say that defines paths by which people can be routed from one location to another. So if someone wants to go from admitting to a certain care room here, you could simply essentially say, okay, take me from that place to this care room, and it will take care of routing the agents along the pathway accordingly. And in the process of doing that, you could assess exposure to various pathogen levels along there, or to air quality levels in the context of sort of outdoor exposures, or exposure to vending machines or other resources. So this sort of modeling provided by AnyLogic, which sort of melds agent-based and discrete event modeling, can be useful for capturing the spatial dependence, the sort of spatial layout in an irregular facility type fashion. So that was a very brief look at three very fruitful types of modeling. Before I go on, are there any questions people have about those sorts of modeling? Bearing in mind this is the retrospective, and I'm going to go on and talk about other things in fact. Any questions? Any conclusions or clarifications you'd like to see discussed about the trade-offs or about the nature of these types of modeling? Okay, so we'll go on. The next major topic that we covered yesterday was the topic of sensitivity analysis, and the key, a couple key features that I just wanted to emphasize was that we can conduct sensitivity analysis in many different ways. The ways which we emphasized yesterday tended to be examination of the outcomes of either varying a single parameter or multiple parameters at a single time, and examining the outcome in terms of model outputs for various sorts. However, we will frequently within these models perform other types of sensitivity analysis. We did look at a case of Monte Carlo sensitivity analysis, cases where we drew parameter values from distributions, and in even cases where we simply ran the model repeatedly to capture the effect of stochastics within the model. Sensitivity analysis is one of those processes that to really have a complete modeling project, you really need to undertake it. Some modeling projects, for example, omit a calibration step. For sensitivity analysis would typically be looked for by those reviewing models as a prerequisite for really showing that you have a good, solid understanding of what the model, how the model behaves. So we saw that within packages we've been exploring in any logic, we have a capacity to perform fairly readily variation of parameter values. For example, examining how parameter values vary systematically over a range. And we can do that with a single parameter value at a time, or indeed with several parameter values at a time. Now, when doing this, to summarize the output from such examinations, we use this construct called a two-dimensional histogram, a histogram 2D in any logic. It's one of several any logic types in a given palette, and it basically provides a way of accumulating the number of occurrences where a certain outcome is then achieved with respect to two different axes, and the binning that occurs with respect to both those axes. So both axes are divided up into these little intervals in an orthogonal fashion, so they're independent of one another. So we have intervals along this axis and intervals along this axis, and this diagram counts the number of cases where, in this case, at times, say between 40 and 42, we experience a certain number of infected in the underlying model. And these 2D histograms provide a way of summarizing model results across many, many runs. Here, the darkness of a given bin, given sort of the squares here, indicates the number of times where we had a realization, a run of the model, a particular run of the model, yield the result that fell within that category. So the darker it is, the more times we saw that. And so it provides a way for us to understand the variability in model output in light of variability in the credit values. And it's automated. I also noted that from the standpoint of performance, running a parameter variation experiment can be a very effective way to reduce model performance, or improve model performance, reduce model computational burden. Because normally any logic models involve quite a bit of reasoning about what's shown on the screen, And if it's put into a parameter variation experiment, it knows it doesn't have to worry about showing every run of the model, what's going on. It just has to summarize the results on the part of each utilization. So it tends to run much faster. It's much less work to do as far as showing things in the screen. So this is an effective way to, one of several effective ways to speed up your model. Okay? Sensitivity analysis. I would highlight one very important point here that I haven't really emphasized, but it bears note. When we have assumptions in our model, we have many options to impose them within any one. If we have an assumption concerning some aspect of the model, it's often tempting to put it in as just a constant into our model. There's many virtues for actually turning it into a parameter, turning it into an explicitly named, recognized assumption. Among other things, that allows us to vary it in experiments. It also allows us to vary it for sensitivity analysis. It also means if we ever go to change it, we can change it in a single place and change it across the entire model. So there's many good reasons to turn what otherwise would be constants in the model, give them a name, make it clear what they mean, another advantage, and then we could vary them in sensitivity analysis or in the sort of experiments we do with what if runs. So this is an important feature of modeling, the ability to run the model at any time. We did see that even absent any parameter variation, even if we were to just leave the parameters at their default values, we still will see some level of variability. I thought I had a nice slide of that, but it looks like I don't. But we did run that yesterday, and we saw there was variability even absent variation in the parameters. And that variability reflected stochastics in the model. It reflected the fact that each run of the model had slight differences due to the vagaries of change control. The fact that recovery time is stochastic, and who you infect or who infects you is stochastic, etc. So to whom we send messages is stochastic, is often stochastic. Our progression through state charts is often stochastic, etc. Okay, any questions about that? Sensitivity analysis? No questions? Okay. The final thing that I wanted to comment on before we launch into today's substantial set of material was a reflection on